Okay, so Paolo, thank you for the presentation. And I'm also glad to be here. This is my first time in Florence, and I have to say, you have a beautiful venue. So today I want to talk about this work in collaboration with Raymond, which is here. And it's really, I would say, the last paper in a series of works about the differential non-commutative geometry of irreducible quantum Flagg manifolds using the differential structures given by Heckenberger and Kolb. So, as the title suggests, today we are going to talk about connections. And let's start from something very non-controversial at all, that is in non-commutative geometry, where we think, thanks to Serre's one theorem, we think of finitely generated projective models over our given algebra A as the space of section of some non-commutative quantum vector bundle. And of course, if A is commutative, in fact, Serre's one theorem tells us that this is in fact the case. So when a first order differential calculus given, Raymond has already defined a first order differential calculus, so I won't bother. The notion of a connection is generalized in a pretty much straightforward way. Let's suppose that we have, for example, a left module over A, then a connection is just a linear map that respects the Leibniz rule, as everybody knows. However, instead of choosing between a left or right module, I might have, in fact, a bimodule. And what happens then is that, in a way, non-commutativity forces us to pick a side. There is no much that we cannot ask to have the Leibniz rule both on the left and right side with respect to both the action that define the bimodule. And the second best thing that people came out with was the definition of a bimodule connection. So let's suppose that I start from a left connection on a bimodule, then I say that this left connection is a bimodule connection if nabla is a left connection, of course, and if this map sigma that goes from my bimodule F tensor omega 1 into omega 1 tensor F, and is defined in this way that you see on the slide. If this map sigma is a bimodule map, then we say that we have a bimodule connection. Notice that sigma is uniquely defined, so this is not an additional structure that I can put on my connection. This is a property that I can check if it holds or not. So yeah, once a connection is given, you only have to check if it is a bimodule connection. And why are these guys important? Not only for a matter of symmetry between left and right action, they are relevant also for me at least, the main reason is that we are allowed in this way to define connections on tensor product of bimodals. So if I got two bimodals F and G, I can extend, and I have bimodal connections on both of them. I can extend my connection on their tensor product. How? In this way, the connection on F tensor G is defined with this formula where on the first part, not much is happening. I'm just evaluating the connection on the first component. While on the second part, first I evaluate the connection on the second component, then I take advantage on the bimodule connection map sigma that flips these two guys. And in this way, I have a non-est connection on the tensor product of these two guys. So we are interested in finding bimodule connections whenever we want to deal with, let's say, monoidal structures of our representations. But so far, there were not many examples in bimodule connections known in literature. In the world of quantum groups, Begg and Majid already produced bimodule connections for line bundles over the Podler sphere, while Marco Matassa did it for the Eckenberg-Cole calculus over the Podler sphere. And in our work, we are in a way generalizing what Begg and Majid have done to all quantum flag manifolds of the reducible kind. Why the ones of the reducible kind? Because as I will tell in a moment, these are the guys for which we have some good differential calculus, that is the Eckenberger and Cole calculus. So let me again take advantage of the fact that Raymond gave a talk before. I will just remind you that if G is a complex semi-simple Lie algebra and big G is the associated compact connected, simply connected Lie group, then then we have two one-parameter families of off algebra that people working at, well, the place that at the time was Leningrad and in Warsaw found during the 80s, studying integrable systems. And we have these two guys, UQ of G and OQ of G, that as Q goes to 1, have a good notion of classical limit in the sense that I get back the algebra of the coordinate function of the group G and a certain cover of the enveloping algebra of my Lie algebra G. And in fact, these guys retain many properties of their classical counterpart. For example, we have a good notion of highest weight representation for these objects. In particular, all finite dimensional representation are highest weight representations. So we can, in fact, play many of the games that we play in unusual Lie theory. And for example, we can define a quantization of the classical flag manifold in a way that follows. So let's consider a subset of the simple roots of our Lie algebra. Then we can define the Levy subalgebras, the so corresponding Levy subalgebras, just by throwing out all the negative and positive simple root vectors that are not contained in this subset and keeping all the case. This is, of course, a subalgebra of UQ of G. Moreover, it actually is an op subalgebra. It's an op subalgebra. And we define the quantum flag manifold OQ of G over the Levy subalgebra of S as the coideal subalgebra of the invariance of inside of OQG with respect to the left action of UQ of LS. So more concretely, what we do is we take the Dinkin diagram of our Lie algebra and we cross out a certain number of nodes in any position, and we take out the corresponding E and Fs, and we consider the subalgebra of invariance with respect to the corresponding Levy subalgebra. And for the ones who know, the quantum flag manifolds are very good examples of quantum homogeneous spaces. Then what Eckenberger and Cole did in 2006 was to find some good quantum deformation of the classical de Rham complex for a subset of quantum flag manifolds, the so-called irreducible quantum flag manifolds that are here displayed in all their glory. So for the AC, all the reducible flag manifolds are actually what you might call like one step or one cross flag manifolds, in which you only cross out one node. In the AM series Raymond was talking about before, you have a lot of freedom. You can cross the node anywhere, one node anywhere, and the corresponding quantum flag manifold that you get is a quantum Grassmannian. And for the other guys, you you can only cross certain prescribed extremal node on their linking diagrams. So these are the reducible quantum flag manifolds, as I said, and Eckenberger and Kolb found that for these guys that are also, they are also called Hermitian symmetric type, because at the same time they are quantum flag manifolds and they are quantum symmetric space, so they have all the regularity that one might ask for. And for these guys, Eckenberger and Kolb found a calculus, a differential calculus of classical dimension, which is exactly the kind of calculi that Raymond was generalization Raymond was talking about before. And this calculus actually exhibits all the possible features that you might ask for. It has non-commutative complex structures. There is a notch map. They also make the quantum flag non-commutative killer manifolds. So since we have a complex structure, we have a notion of holomorphic and anti-holomorphic part calculus, and we are interested in studying the connection over the line bundles on the quantum flag manifolds with respect to the anti-holomorphic part of the calculus. So one more technical object that I have to introduce before is the quantum Poisson homogeneous space, which is defined just by taking the semi-simple part of the Levy subalgebra. That means instead of throwing away just the E's and the F's that I have crossed out, you now throw away also the corresponding elements in the Cartan subalgebra. And the quantum Poisson homogeneous space is the space of invariance with respect to this smaller subalgebra. And in fact, since it's the space of invariance with respect to a smaller object, is a bigger space. And yeah, as I said, they call this guy the quantum homogeneous Poisson homogeneous space associated to the system of simple root S. Why was this object important? Because it allows us to classify relative line models. So a line models or line bundle, I feel free to use the two terms in an equivalent way. A line bundle over B is an invertible B bimodule, in the sense that there exists for E, if E is a line bundle, then there exists a dual to it in such a way that I can tensor over B on both sides, and I get something that is isomorphic to the base. And a relative line modulus over a quantum homogeneous space with respect to an off algebra A is a B sub bimodule, which is also a left A comodule. And also we require that these isomorphisms are isomorphisms in the right category. So in the left A comodule, they are also left A comodule maps. So we have this nice proposition that the quantum Poisson homogeneous space actually decomposes into simple subobjects that are the line bundles over my quantum flag manifold. Fantastic. And what a bunch of people from Prague, so Freddy, Diaz Garcia, Andrei Krutov, Raymond, Peter Somberg, and Karen Strung found is that for every relative line module, they found that there exists a unique unique connection which is covariant on the left with respect to the coaction of OQG. And what we did in this work was to give an explicit construction of this connection using the theory of quantum principal bundles and principal connections. Of quantum principal bundles and principal connections. So I won't tell you anything, I guess, about quantum principal bundle due to the lack of time. Just take it as a black box that, as a theory that allows me to define connections on associated vector bundles. Sorry? The connection, yeah, it's flat. It's double flat, yeah. Yes, thank you. Then when you project on yes. The other one, yeah. Yeah, thank you for pointing that out. So what we found is, first of all, that we actually have a quantum principal bundle, as you would expect. The quantum, we have a first order differential calculus on the quantum Poisson homogeneous space that restricts to the Eckenberger and Kolb calculus. And with this choice, we have a quantum principal bundle. Not only, but we also have a covariant strong principal connection that is just given by the zero map on the horizontal forms here. And what we have is that we can use this data to construct on each, yeah, I forgot to tell you that these guys are Z-graded, but yeah, they are vector bundle. As a matter of fact, they are Z-graded. And on each line bundle, we can just define, we can use the theory of quantum principal bundle to define a connection in this way. So I just take the differential of E, and then I use the fact that the multiplication map here from omega 1b tensor EK is an isomorphism. And one can now check direct. First of all, this connection is by construction left OQG covariant, and so it coincides with the unique connection we were talking about before. And for each line bundle, this should be partial K, but okay. So the connection is a bimodule connection, and the associated bimodule map is an isomorphism of OQG comodules. Now, okay, this is the general theory, how we compute the action of these connections. We found a way that combines both Lie theory and the theory of quantum homogeneous spaces by making use of what we call generalized determinant relations and Takeuchi equivalence. I guess I have still 10 minutes, right? Yeah. So first of all, the two first line bundles are generated by two highest weight vector Zn. Prova. Messo al contrario? Ah, no. Be back soon. All right. Thank you. We have, thank you. We have two eyes with vector that generate E1 and E-1, and we can produce from these two a dual pair of irreducible UQG modules just by multiplying on the left by UQ of G. And since these two guys are dual, their tensor product will contain a copy of the trivial module. So we can, this means that we can find pair of elements such that this, the sum of these products is equal to 1. Then we can, in fact, what we can do concretely is to take the definition of the bimodule map sigma and basically multiply by 1, which means we plug in these elements that we have found. And we have this presentation of the bimodule map, which for as it is now, doesn't look particularly interesting. But if we look at concrete, let's look at a concrete example like the Potter sphere. Here, the generalized determinant relation is, one good generalized determinant relation is the quantum determinant. And in fact, we can have this presentation of sigma for the first vector bundle that, that looks in this way. So we have all the generators of quantum SU2 appearing inside of the map sigma. And okay, we can actually do better by making use of Takeuchi equivalence. So by Takeuchi equivalence, in fact, we have an equivalence of monoidal categories between the category of relative of module of QFG or QGLS, where here mod 0 means that if I have a module inside this category, let's call it F, where here the plus means that we're considering elements inside the kernel of the co-unit. And if this condition holds, we have a Takeuchi equivalence is an equivalence of monoidal category, where here where on both sides we have on one side we have the tensor product of OQGLS bimodule, and on the other side it's just the tensor product of OQLS left comodules. And as a matter of fact, all the line bundles over the reducible quantum flag manifolds, together with the Birkenberger calculus, live in this category. So we can make use of the monoidal structure we can make use of the local of Takeuchi, of the monoidal version of Takeuchi equivalence. And it's actually quite easy also to verify that the map sigma that we have found before is in the same category. So this means concretely that we can describe the map sigma locally on the fiber. And what happens is that if I look at the image of sigma inside the category of left comodule with respect to the Levi subalgebra, the map sigma just gives me a flip up to a constant. So what is happening here in fiber by fiber is I just get the classical case, that is I flip the first order calculus and the modules up to some constant. And if now we work furtherly on the positive sphere example that I was telling you about before, what we find is that locally, my bimodule map is just the flip of the elements inside of omega 1 and the elements inside the line bundle up to the constant q to the minus 1. Then we can just use the Takeuchi equivalence to go back to the category of relative host module. And this is how the full map sigma looks like in general. So it's kind of convoluted. We are using the coaction, and we are also the antipode is involved, but as it should be, if we consider the commutative case, we found out that in fact this map coincides just with the flip of the two guys in the classical case, as it should be. So 2 words about the possible applications in the future. First of all, it will be nice to extend this proof from homogeneous line bundles over reducible quantum flag to the line bundles over every quantum flag, or in general to the homogeneous vector bundles over any flag. Then probably, since this allows us to describe the connection over the tensor product of modules, we can make use of it to prove a quantum version of Riemann-Roch theorem. Finally, a more far-reaching project will be, Raymond today was telling you about geometric representation theory. So in a way, we can realize the representation theory of a quantum group by looking at sections of a line bundle, but maybe the fact that we can, in a way, now give a differential realization of the model, maybe we will be able to use bimodule connections to give a realization of the monoidal structure itself, but it is not even just, it's really a work in progress in the very beginning. So that's a story for another day. And for now, thank you for your attention. Sorry, yeah, we, okay, this is another, but yes, we, you have a quantum version of the Borel-Well theorem, so you got irreducible representations. Yeah, we prove it for the Eckenberg-Cole calculus, and Raymond today was telling about the version for the full flag.